Example 11 from chapter 1, and this 11 and 12 are the last two examples of chapter 1. So after this lesson, we're done with chapter P and chapter 1. Quiz is happening next week. This is a quadratic inequality, and this is something dealt with at the very end of Algebra 2, probably the last 10 lessons or so of Algebra 2. And the technique I use to do this involves factoring. It also involves interval notation and some testing of intervals, which is something that's kind of a new idea to most people. The challenge here, or the technique that I'm going to use here, first off, is I'm going to take my polynomials should be either greater than or less than 0. You always want to compare to 0. You never want to do anything but 0. All right? Because 0 is easy. Everything else is more challenging than that. And what I'm going to do is I'm going to pretend it's equal to 0 to begin with. And just solve that and figure out where it actually equals 0. All right? And I think the problems in your homework, this one obviously, but the problems in your homework I think are all going to be factorable expressions. If they weren't factorable expressions, quadratic formula can find the answers for you. But I would expect them to come out to pretty friendly answers. If it's a harder factor type, such as one that has a 2 or 3 or 4 in front of the x squared, then maybe the quadratic formula maybe get some fraction answers out of it. But they should all have pretty reasonable answers. You're not going to get like 7 plus or minus the square root of 15 over 3 or anything like that. So they'll be just 1, -4, 2/3, like that. So again, if it's one with a coefficient in front of x squared, maybe use the quadratic formula, but it should get a nice square root that works out. In this case, we end up with x equals -4 and +1. Now, what we're trying to figure out is what range of x's create a true statement for this inequality. All right, so they create a negative product, or a negative number here, because less than 0 is negative. And what these two numbers represent is the two numbers for x that create an answer of 0. All right, and the cool thing about 0 is if you're going along a graph, and let's say you're up here in the positive range above the x-axis, the only way you can get below the x-axis is to cross through 0. Okay, so that's the theory. If I can find out where it equals 0, then it's either going to be positive switching to negative, negative switching to positive, positive touching and going back up to positive, or negative touching and going back down to negative. Those are the only 4 possibilities. So I found where it equals 0. That's the only place the sign changes can occur. So if I'm at positive, and let's say 0 is here, I'm still at positive, I'm still at positive, still at positive, still at positive. Now I'm at 0. Maybe now I'm at negative. So I don't have to test millions of numbers. I can just say this region is going to have all the same sign, this one's going to have all the same sign, and this one is also. So that's what I'm doing here by setting it equal to 0, is establishing where sign change can occur. Then I go on to create intervals. Every number line goes all the way down to negative infinity, ends at positive infinity. So what I want to do is set up intervals all the way from negative infinity to positive infinity, including every stopping point, which represents any place x equals, or any value of x that creates a value of 0 for the function. So negative infinity to the smallest number in the list, -4. Notice I did use a parentheses for the negative infinity. I'm also using a parentheses for the -4 because it's just less than, it's not equal to. If that had said equal to, I would have had a bracket here. Still a parentheses on the infinity though. Alright, the next interval that I'm going to deal with goes from that same number to the next bigger number, which is 1. And once you run out of numbers, you go from that last number up to positive infinity. So just to give you a visual of what's happening here, let me just use some different colors too. So all the way from negative infinity to -4, some sign occurs on that function. I don't know what that sign is yet, we'll find out in a minute. All the way from -4 all the way to +1, some sign occurs. And all the way from 1 to infinity, some sign occurs. Okay, so what we've done by finding these two zeros, the roots, we've created now, just based on there's only 2 places signs can change. There's some sign here, then the sign could change. There's some sign here, then the sign could change. There's some sign here. So I've created a situation now where I can just test the intervals. The only requirement for testing an interval is that you pick a number that lives in that interval. Okay, so go back to the old playground game, pick a number between 1 and 10, right? And instead of this one is pick a number between negative infinity and negative 4, all right? I'm going to pick negative 5. Pick a number between negative 4 and 1, I'm going to go with 0. Anytime I can pick 0, I like to because 0 is easy. Pick a number between 1 and infinity, I'm going to pick x equals 2. I could pick negative 5,975,742,867.5634 pi if I felt like it. Negative 5 is a lot easier, right? So it doesn't matter what you pick, just as long as it lives in that interval, it will test that interval, it will give us a value, okay? The only thing I care about on that interval is the sign of the answer. I don't care about anything but the sign of the answer. Now the easiest way to do this without a calculator, we have our factored form for the expression, right?
Okay.
So if I go to the factored form, I'm multiplying two numbers, right? Again, I don't care about what the number is, I care about what the sign of the number is. So if I put negative 5 in place of x for both of these, negative 5 plus 4 is negative 1. Negative 5 minus 1 is negative 6. Negative times negative makes a positive. So this interval here represents all positive answers. All right? And again, all I tested was negative 5, but every other number has to have the same sign because no sign change happens until we get to negative 4 equals 0. So everything there is positive. Doing the same thing for 0, again, I've got two things being multiplied here. 0 plus 4 is positive 4. 0 minus 1 is negative 1. Positive times negative makes a negative answer. So this entire interval here is negative. And finally, with x equals 2, I make my two factors. 2 plus 4 is positive 6. 2 minus 1 is positive 1. Two positives makes a positive. So this entire interval is positive. All right? So that's all testing intervals is. Once you've done all that stuff, you simply have to figure out which ones of these answers, plus or minus, make this inequality true. Less than 0 means negative, right? So we're looking for negatives. This is the negative interval, right?
Okay.
So all I would do then is I would say, as far as an interval answer is concerned, let's try that again. There it goes. This is the correct answer in interval form, negative 4 to 1. This is the correct answer in graph form. Okay. And in general, just do what the book asks you to do. If it asks you to solve it, there's the answer. If it asks you to graph the solution, there's the answer. All right, so this is the solution, this is the graph of the solution, depending on what they're asking us to do. All right? If it said greater than 0, then both of these would be the answer. And you would do this union with that, and you would graph negative 4 to negative infinity and 1 to positive infinity. Okay? The technique's the same whether it says less than or greater than. All this stuff's the same. The only difference is what answer is right, plus or minus. Less than 0, minus is right. Greater than 0, plus is right. If it has equals to, you put brackets instead of parentheses. You put closed circles instead of open circles. So every scenario that could possibly occur can be dealt with pretty easily using this entire technique every single